Okay, so thank you for that. My name is Melda. I'm a PhD student at the Center for Advanced Spatial Analysis at UCL. And what I'm going to talk about today is a paper that I worked on, a research project where we looked at Google Earth Engine's potential to fill in critical data gaps in the developing world. And for this purposes, we focused on Lebanon. So before I get into Google Earth Engine, in case you're not kind of aware of that tool, I'm first going to talk about critical data gaps. So I'm sure we've all experienced problems with data. There are gaps in data in all sorts of different data sets, but what I'm most interested in looking at is data gaps at the kind of at the national scale, or critical data gaps that really prevent policy making in developing countries. So here on the left, there's an indicator by the World Bank that measures statistical capacity in the developing world. And as you can see, the countries that are in red are kind of below 50 in this indicator. And there's a pretty strong correlation between countries where there are conflicts, like we see Libya, Syria, Iraq, all in red. So there's a strong correlation in places where there is conflicts and therefore vulnerable populations and the lack of good data. So that's the where. And then if you look at Lebanon here on the right, so, the curve is in light blue. We see that generally it's kind of hovered around that 50 out of 100 mark, but with it increased for the most part. But then a couple of years ago, when there was a big economic crisis and political crisis, statistical capacity decreased dramatically. So this also shows that like where we need good data in order to kind of serve vulnerable populations, and then when we need it most urgently, we don't get the data that we need. So it's a pretty critical kind of problem just across the developing world, and I'd say many parts of the developed world. So I just want to deep dive a little bit into Lebanon to explain the context a bit more. So Lebanon was created in 1943, but the last census was actually in 1932, so before the country even existed. So that means that there's really hasn't ever been a proper full population study of any sort. So even population numbers are estimates based on voting records and births, etc. Almost all the data that's being used in the country is based on estimates when it comes to population level stuff. And kind of coupled with the lack of just national data, there have been many waves of refugees across, since the country was created. So there's about 250,000 to 500,000 Palestinian refugees that have been around for decades. And you can see this kind of map on the right. The triangles show where the Palestinian camps are. And then over the past 10 years during the Syrian civil war, there have been what's estimated about 1.5 million Syrian refugees. The official numbers are a bit less because not everyone registers, but that's just kind of the scale of the volume of kind of increase in population that happened. So currently the population is about 6.8 million, so about a quarter are refugees. And that all happened, kind of the big wave increased over the past few years. So it's significant strain on infrastructure, and many more vulnerable people are in the country. So it's almost like you're driving blind, almost if you know where people are or the extent of vulnerability. There have been really fantastic efforts by different organizations. We do get maps like this one done by GISRUK in 2016, but there is still quite a significant lack of data. So what that ends up meaning is that now we have the highest refugee per capita rate in the world, and that's coupled with the current economic crisis. So for most of my life, the currency was about 1,500 Lebanese pounds was $1. And then over the past 5 months, since about December until now, that's jumped, as of this morning, it was about 8,100. So huge currency devaluation, coupled with some inflation as well, and just kind of general economic crisis. So, in a place where there isn't data kind of from the beginning, and when there is an economic crisis, how do you then deal with the situations that you have to? So what I was interested in looking at is, can satellite data be used to fill in this gap? And I'm not sure how many of you are aware of the different satellite data. So here's kind of a nice visualization of Earth observation satellite, specific type of satellite that orbits the Earth very close to the Earth, so low orbit, and it just orbits continuously around. So you end up getting kind of you stitch together a map of the world when you collect images or different sorts of data, which then helps. You can do quite a lot of. Sorry. quite a lot of analysis with this. I'm not going to go too much into it, but I just wanted to give a really quick overview of the different Earth observation data available. So there's passive and active. Passive satellites are the ones, or sensors are the ones kind of like a camera, where like the things that we're used to on like Google Maps or Google Earth, where you're just kind of taking a picture of the Earth as it orbits. There are also active satellites which emit radiation and then collect the backscatter. And the benefit of this is you can like see through cover or in areas where there's a lot of snow. There are specific applications of active satellite data. I'm not going to look into that, but I just kind of wanted to make people aware of that. Another reasons kind of why we would use Earth observation data to potentially fill in critical gaps. There are several reasons. One, we have the global coverage, because once you launch a satellite in low orbit, it just continuously orbits Earth. So even if a small country can't afford to launch an Earth observation satellite, it can benefit from the ones launched by kind of richer countries that have that capacity. Temporal coverage. The NASA Landsat program has been running since the 1970s. So even if you wanted to do historical analysis, that's all available, which is really fantastic. And kind of more modern satellites are now, you can get almost daily or even sub-daily imaging. So near real paths is also an option. High spatial resolution. So the more modern satellites are now collecting the spatial resolutions up to 10 meters for freely available images, like the national ones, and even up to 30 centimeters through private companies. There was a talk earlier today by C. Jiang using a very high resolution satellite and land cover and land use classification. It's really interesting. Publicly available. So I think about a decade ago, a lot of the Landsat data was just made free. And there's a great paper that showed that the shift towards the open and free data policy enabled many innovative studies. So this trend is kind of growing, which is pretty fantastic. And there's a very wide range of applications. So there have been many studies that have used Earth observation data for refugee camp monitoring, soil mineral analysis, forest fire detection, deforestation, etc. These are just examples that I've seen done here. So there's just a huge range. Here are a few other ones that I wanted to highlight. You can use Earth observation satellite data to monitor natural disasters. Like you can see where there's a forest fire, so burn scars, land cover maps. I'm going to dive into that, so I'm not going to talk about it too much right now. NO2 emissions. So you can, I'm not sure if any of you have seen the kind of before and after images of like the COVID lockdowns and how much that impacted NO2 emissions, but that's also collected from Earth observation sensors. And this was just a quick visualization that I built. So you can look at before and after for any part of the world, really. It's online, so I can link to it if anyone's interested. Population, so using nightlight images, which is a really cool data set, and different sorts of data. There have been a very impressive population, kind of global population estimates available. So you can see where people live exactly, and to pretty decent spatial resolutions, and how many people live where. So the kind of unmapped or people that live in rural areas or in developing countries that aren't really kind of taken care of by their governments, you can at least get that information available. Using the active imaging, some cool applications are like detecting unknown vessels in the sea because of the backscatter that's available. And then finally, just one more thing I wanted to highlight is for the very high resolution imagery, there's a company that pretty much exclusively looks at the shadows of oil silos across the world, so they can see where, like, how much oil a country has reserves, which says a lot about their preparedness for different crises, and kind of lots of different indicators you can get from that. So, however, there's a lot of potential, but there's quite a lot of challenges as well. So you need to know that the data exists. You need to know how to access data, the different file types, the data formats, etc. Specialized skills. You need to understand kind of the quality measures that are kind of associated, understand how to process rasters, etc. Compute power. These files are huge, so processing is very complicated, and you need to be able to download these images. Like I've been in Lebanon for the past month, and each time I want to download a single image, I get so many timeouts. So just downloading one satellite image often takes me. So there are significant disadvantages as well. And that's where Google Earth Engine comes in. So in a nutshell, GEE is a cloud-based geospatial processing platform. almost all the publicly available data sets are there to use, and you can process them on the platform, so you don't need to download anything to your computer. Lots of compute power is made available to users. I've never had a problem with compute power, and if you have like a big project you want to run, the team is actually very flexible, so you can email them and they'll give you even more compute power for free, or free for researchers, which is great. On the platform, which I'll show you in a second, you can process data in JavaScript online, or there are also Python APIs. And now, since this tool has been around for a while, there are many users that have developed libraries to link to R and kind of lots of different things. So quite a lot of potential to use it. And the code editor, which I will show you here, is very user-friendly. I learned how to use it just kind of through trial and error. So if you get an account, you go to code.googleearth.com. This is what you see. So you can write, I think I can move my mouse, yeah. So you can write your code here, run it, and then it will, any maps or visualization will show immediately. Really impressive processing times. You can print out anything to the console or kind of inspect the image. And what's great is that there are a lot of scripts ready to go. So a lot of what I learned was just going through the different scripts and figuring out what I needed, and the documentation is right there. So it's an impressive platform that I would recommend people to check out if interested. So now to land cover. So why am I interested in land cover data? So I wanted to look at something that could be done using satellite data that would be very useful to developing countries. So I chose to focus on land cover at the, for the first part of this research. One, because it's an essential climate variable. So as is, land cover is very useful. And it has kind of been deemed an essential climate variable by different organizations, because you can see land cover trends over time to see climate change, etc. So kind of standalone, it's useful, and it's as an input for many other purposes. So cropland monitoring, food security, which is pretty important nowadays, urban sprawl to see kind of where people, how like urban areas are growing, change detection, deforestation, etc. So there's quite a lot of uses for land cover. Global land cover maps exist, but there are quite a few spatial data quality issues. This is kind of a brief kind of takeout from another paper we have about spatial data quality evaluation, specifically for land cover maps. Kind of in a nutshell, that there are these really great maps that are being produced and have been produced for a while. Most of them have a pretty coarse spatial resolution, so about 100 meters to 500 meters. It's very coarse, especially for small countries. And the temporal resolution is usually about yearly, but often it's once per year, but not every single year. So those are significant limitations. I do want to point out that there's a really kind of impressive land cover data product done by a group in China that's at 30 meters resolution, which is really, really impressive, but it's only at 2 different years, so it's still limited temporally. So I'm not going to go into this further, but as I mentioned, coarse spatial resolution, temporal resolutions, the 1 map per year, so you don't really know, was this map produced in the growing season? Typically it's composite images, so 1 pixel might be from March, the next could be from September. So there are a lot of kind of inaccuracies that could come out of these global once-a-year images. So what we wanted to do is research, can we use these data sets, the methods, the free-tier researchers' compute power to produce fit-for-purpose land cover maps? And if so, what approach produces optimal results? And then how can we also apply that to multi-decade data sets, which would be pretty impressive and cool. So what's great about land cover classification is that different surfaces have specific reflectances. As I mentioned, the passive imaging doesn't only collect the red, green, blue that we see as humans, so different parts of the spectrum, and then different materials, earth land covers, reflect the sun in different ways. So each kind of material has a spectral signature. And with kind of the onset of machine learning is that you can create a data set and train a classifier and apply it to capture that information. So what I ended up doing is I first created a training data set using Google Earth Engine. So literally dropping points, like zooming in on very high resolution imaging and putting different points on urban and built up, on forest and cropland. And then I compared that to the global land cover product, one of a MODIS land cover products. And kind of the general workflow is that, so first I created that training data set. And then I just took in Landsat images. I chose the least cloudy image I defined, well, here it says per year, but I took over a specific couple of months which represents the growing season. I masked the clouds, selected different bands, added NDVI, which is a vegetation index, added elevation and slope, and then randomly sampled the training data, made a classifier. So I compared these 3 different classifiers, and I'll show you that in a second. And then classified input imagery, and assessed using also randomly sampled data, assessed accuracy to get different results. So what ended up, so here's the accuracy results, and I'll show you the maps in a second. Just checking the time. So as you can see, what it ended up doing is comparing random forest, CART, and support vector machines as classification methods and different inputs. And the reason I kind of went with these different inputs are based on different papers that I've seen, that some used only specific bands, some added in other bands, and DVI and elevation, etc., to see what uses the optimal input type kind of data to get the highest accuracy results. So the top part is using the points data, the one that I built, and this is using the MODIS training data. And as you can see, well, first in both cases, random forest produced the best results, and adding in elevation and slope helped create even more optimal results. But generally, in all cases, using the points data did produce better results compared to the MODIS training data set. And here you can see some of the maps that were created using the different classifiers and the different training data sets. Since MODIS has many more land cover classes, I merged a few to be able to compare with the points data set, which, since it was kind of visually made, I couldn't go into anything more granular than barren, urban, forest, etc. What we see is that the points data has a lot more urban classified. The MODIS overestimated some of the vegetation. So it's difficult to see which is really the ground truth, because there is no proper land cover map done by the government, which is like a source of truth. But you could kind of argue that the points data is closer to truth because it's almost like ground truthing. So rather than kind of walking around and building a data set using a GIS handheld tool, we did it just kind of by using very high resolution imagery. And then we applied the classifier to maps or land cover, satellite imagery from the past, all the way, well, here I just show 1985, but you can go even further than that, which is really cool. So you can see land cover over time. I still think that this requires quite a bit more research, because it doesn't really make sense to me that there's this much urban area back in 1985 and less in 2017. But also there was a civil war then, so I'm not really sure. But it's an area that would need further research. But it's really cool to see that the tool, Google Earth Engine, and the methods that we use can produce land cover maps. So now it's just a matter of refining it further. And then here's the same thing for MODIS, and you can see some inaccuracies where the 2 different images overlapped. So that's something to work on. So just to conclude, so back to the research questions, Google Earth Engine did prove to be a very useful tool to be able to produce land cover maps for a single year or over time. The random forest classification method and fit for purpose training dataset produce optimal results. And there's quite a lot of potential to even fill in other critical data gaps, which is what I'm looking at in my PhD work, so beyond just land cover. So in my research, I'm looking at how can we estimate economic indicators globally using satellite data, both kind of pre-processed products like imagery and different more processed data sets that are now available from the different agencies, like land cover change or population estimates through satellite data, or nightlight imagery is a pretty interesting data set that's now available. So that's kind of what I'm researching for PhD. And I also want to highlight another project that I'm working on, also using Earth observation data, where we're taking flood risk data and and seeing how many people are exposed to FLEDGIS data across the world. And we've actually already gotten the results. It's a project that's being done with the World Bank, and it just kind of shows that, you know, the standalone data sets are useful, but then when you combine them, you can get a whole host of other information about where people are most exposed, the poverty. If you have poverty information, then you can see where poor people are most exposed to flood risk, etc. So kind of in conclusion, there's a lot of potential to use satellite data for to fill in critical data gaps. And these are just kind of one example of what I've been working on. I would be happy to take questions and kind of feedback or ideas if anyone has any. Okay.
Great. Thanks, Melda, for an excellent presentation. You can stop sharing if you want. There is that stop button. You see there's a circular icon with a square on the...
oh, yeah.
Yeah.
Got it. Excellent. Thanks.
So the audience are invited to type the questions. So first question from Hannah. Can we see that land cover changes over time using Google Engine 2? How often data are updated?
Yeah, you definitely can. So if you were to use the pre-existing global data sets, like if you didn't want to do classification, etc., it would just be comparing a yearly image to the one before. So you can definitely do that using Google Earth Engine. So that would be a 1 per year image. The data on Google Earth Engine generally is as soon as it's available, like published by, let's say, the European Space Agency, it's usually on Google Earth Engine pretty quickly. So in terms of update, but if you wanted to make your own, kind of like the classification one, I mean, it depends on the input data you use. So I was using Landsat, and that's about once every 14 days. There are other optical imagery that's a much faster time. So, you know, it depends on what your needs are.
So more questions flowing in.
Okay.
So Stephen Law is asking, did you consider any pre-trained model for predicting land cover? Does your model generalize to adjacent regions?
So for the first question, no, I didn't, but that's a great idea. I'm going to look into that about using pre-trained models. Does it generalize to adjacent regions? I haven't applied it to, so adjacent regions doesn't impact the way it works now, but if I wanted to apply it to any adjacent region, it would just be a matter of changing the region of interest, which is pretty easy to do.
Great. So next question from Paul Esner. Excellent talk. Did you test Sentinel data for the years when parallel Landsat Sentinel data is available?
No, I didn't, but that is something that I wanted to do. I focused on Landsat for this project just because of the temporal range, just to be able to go back to the 1970s. Sentinel, so Landsat, for if anyone doesn't know, has very long-term imagery, but the resolution, the highest resolution available for the most recent ones, about 30 meters, while Sentinel is the European Space Agency optical imagery program, and that's up to 10 meters resolution, which would be really interesting. And I was considering trying Sentinel to add in some like object detection as well. So I think that would be the next stage of research, and then to compare it back to Landsat would be really interesting.
So next question from Labib. Are training data multi-temporal, such as for each time you have different sample points? If yes, how did you know which land cover is which? Did you compare visually with other data? And then there's a second question. So let's start with the first one.
Yeah. So currently the training data set. So when I was doing this, the most recent MODIS land cover map was 2016. So I used Landsat imagery from 2016 to create the training data set, just so they're at least the same year, and then use those two training data sets to train the classifier, and then applied the classifier back in time. But I don't have, that's why I didn't calculate validation or accuracy data for the historical imagery, just because I mean, I could potentially do it if I were to create a training data set for each year of interest. But as it stands now, it was just kind of that's what really looking at 2016 and then just seeing can we apply that classifier back and get kind of reasonable results, which we at least got maps, which is pretty great and that look more or less okay. But to actually get accurate maps to see, that's why I didn't really focus on land cover change over time using this, because I still haven't trained anything specific for kind of 1985. But that is definitely something that I'm looking at doing next as well.
Great. And the second half of the question is, are you considering even higher resolution data for the future, such as Sentinel-2?
Yes. Yeah. As I mentioned, I'm definitely interested in using the Sentinel-2 data, and even if possible, some of the much higher resolution data through Planet and Digital Globe, etc. And I think for those, it would be, we could use the methods as are, but I would be really interested in looking at object detection as a way to further improve results. So that would be a next phase of research.
Great. So I have one final question. So you talked about land cover classification, and that's something that intuitively one can understand that from remote sensing data you can reach land cover classification. When you want to estimate economic activities, I'm familiar with something like you mentioned night lights detection, or I would imagine also detecting objects such as power plants or factories. So what are your ideas about the limits of this kind of data for economic indicators?
There are definitely limits because so that's the difference between land cover and land use is, I mean, for land cover you can detect if if there's a building there, but it's difficult to detect if it's being used by a financial services firm or like a shopping mall. So to really, in urban areas, I think that will be the most challenging part, which is why I think the high resolution data could offer a lot of potential. So I'm thinking that proximity to infrastructure could be interesting. There could be an interesting kind of prediction there. What I've been kind of considering lately is land cover change as a prediction. So if there's like the extent of change could predict economic activity to an extent. So that's something I'm looking at as well, and maybe combining it with other data sets. So maybe the like nitrogen NO2 emissions that indicate that there is economic activity. That's also so just looking at different things. I think a big part of the research that I'm planning on doing is finding all the potential predictors that I possibly can, and then do kind of a principal component analysis to see what is actually the biggest predictor. So nightlight imagery has kind of stagnated for a while about the amount that you can predict, but then now there have been some studies coupling nightlight imagery with land cover classification and different stuff that showed that you can get even better results by combining the two. So looking in those areas.